Hi, I'm Matan, and this is Memories of Forgotten Concepts. This work was done with Shimon Malnik, Amir Yevnisek, Oad Fried, and Shai Avidan. In this project, we explore how well current concept erasure methods work, and as we'll show, they often don't truly erase the targeted concepts. Diffusion models are powerful, but they can also generate unsafe content, like violent or explicit images. To mitigate this, recent works have proposed concept erasure techniques that aim to remove specific capabilities from the model. Let's start with the problem. Suppose we have an image from the concept church. Now, suppose we want to make the model forget the ability to generate this concept. In practice, previous approaches stopped the generation of the concept only in some cases. We showed that we can reconstruct the original image even though the concept was erased. This shouldn't be the case, right? Previous approaches have tried to interfere with how the model refers to the text. This way, the model no longer associates the target prompt with the concept. Instead, we query the latent space given the query image. Our approach was to use inversion on an image from the erased concept to find the seed that will generate it. However, inversion alone is obviously not enough. It is important to verify that we can reconstruct the images from the target concept. And indeed, we showed sufficiently good reconstructions for all concepts and erased models we tested. Okay, so we found a potential seed, but maybe it's very unlikely, meaning the chance the model would ever sample it is very low. So how likely is it to actually sample this seed? We analyzed the likelihood of generating concept images compared to arbitrary images. First, we expect a good forgetting method to maintain the likelihood of generating normal images high. This is because we don't want the model to forget how to generate valid images during the forgetting process. Also, we would expect from a good forgetting method to reduce the likelihood of generating images from the erased concepts. So, if a model has truly forgotten a concept, the forgotten group should be far from the normal distribution, while the reference group should stay close. We translated this idea into a reasonable measure. The larger this ratio, the better the forgetting. The problem is that across all models and concepts we tested, the likelihood of our seeds are as high as that of random images. That should not be the case. So, we can generate erased concept using likely seeds. But is there just one plausible seed per image, or are there multiple? We showed that we can take arbitrary support images and use them to generate different distant seeds, all of which reconstruct the same target image. We use each support image as a starting point to retrieve a different seed of the target image. Since we start from random support images, we end up with multiple distant seeds, or memories, of the same target image. And as before, we analyze their likelihood and reconstruction quality. To measure how distant these memories are, we compute the average pairwise cosine distance between them. On the right, we show a stress test. We took a single image from an erased concept and extracted 1000 different seeds for it. So there are much more memories than a single one. This result led us to ask, is real forgetting even possible in diffusion models? We pushed this further with the following example. We took a model that had supposedly forgotten the concept church. We took a church image and scrambled it. Then we performed inversion and reconstruction. When we then descrambled it, we got surprisingly decent reconstruction. This suggests the model can reconstruct images it definitely didn't see during training. So, do we need to forget what we didn't even see? And the key question remains, is forgetting in diffusion models even possible? To conclude, we showed that current concept erasure methods often fail silently. The model can still generate the erased concept with high likelihood. And not just through one specific seed. We consistently find many distant and likely seeds for the same image. These findings highlight the need for likelihood-based evaluations, which will hopefully lead to safer models. Thank you for listening.